Hello class, in this lecture we will be discussing fluid flow in pipes. So what are pipes? Pipes are conduits through which fluids flow, either liquid or gas. Pipes are very useful in conveying fluids. Also, conduits may flow full or partially full of these fluids. So now, what are the losses or head loss that we may encounter here, and how do we compute it? So in computing the head losses in pipe flow, we have several formulas that we can use. We have the Darcy-Weisbach, the Manning, and the Hazen-Williams. The first one is the Darcy-Weisbach formula. It is also called as the pipe friction equation. So the formula for Darcy-Weisbach in computing the head loss in a pipe is FLV squared over D times 2G, where F is your friction factor, L is the length of pipe, D is the pipe diameter, and V is the mean or average velocity of flow. So we can also express this head loss in terms of flow rate. So if there is a given problem where the flow rate is given, we can directly solve it using the discharge itself and not converting it to the average velocity. So if we are going to use the discharge, here's the equivalent formula for the head loss using Darcy-Weisbach. So that's equals to 0.0826 F L Q squared over D raised to 5. Okay, so this is in SI units. Next is the Manning's formula. Manning's formula is commonly used in open channels, but it is also applicable in finding the head loss in a pipe. So the formula for Manning's in determining the head loss is 6.35 n squared L V squared over D raised to 4 third. That is in SI units, where N is the roughness coefficient, L length of pipe, D pipe diameter, and V is the mean average velocity. So using flow rate again, here's the equivalent solution for the head loss using Manning's 10.29 n squared L Q squared over D raised to 16 over 3. And the last one is we have the Hazen-Williams formula. So in Hazen-Williams formula, we have formula of H of F equals to 10.67 LQ raised to 1.85 C1 raised to 1.85 D raised to 4.87. C1 is your Hazen-Williams coefficient, L is the length of pipe, and D is the pipe diameter. Okay, so here are the three formulas that we use in solving the head loss in a pipe. Okay, so now when we have pipes connected in a series, so we have more than one pipe. So given that we have three different pipes with different sizes, different diameters, um, the relationship between the flow rate as well as the head losses can be represented by the following. As you can see here, in order for us to obtain the total head loss, okay, so since it has different dimensions and it has different lengths and diameter, so it will give you different values of head losses. So it means that if we are going to determine the total head loss in this pipe series, we have to add all the head loss on each pipe. using the formula we discussed earlier. Now, for the flow rate, as we have discussed this on our previous lectures, if we have pipes connected in series, regardless of their dimension, of their diameters and lengths, their flow rate remains the same due to the conservation of mass. Okay, so it means that the flow rate at point 1, pipe 1, pipe 2, and pipe 3 are equal. So next, if we have pipe connected in parallel. So for parallel connection, say here is your inflow and your outflow as at this point. So this discharge Q in the inflow, when we have three parallel pipes, okay, is divided into three pipes. So it means that this discharge Q is equals to the sum of the flow rate. So it means that the flow rate on each pipe are distributed from this flow rate from the inflow discharge. Okay, so this Q is distributed on Q1, Q2, and pipe 3, pipe 1, pipe 2, and pipe 3. So that's why discharge Q is equals to Q1 plus Q2 plus Q3. The same way, considering this point of connection between the three pipes and going to the outflow, so our outflow discharge Q is just the same as the inflow. Okay, and then we can simply say that the discharge at Q1, Q2, and Q3 is just equals to the discharge on the outflow. Okay, but the discharges on Q1, Q2, and Q3 are not the same. They are not equal because it will depend on the value of your diameter and other factors such as their friction factor and their lengths. Okay, so the values for the discharge on each pipe will vary, but the sum of their discharges should be equal to this Q right here on the inflow or either on the outflow. Okay, for the head loss, unlike discharge where the discharge on the inflow is distributed, in the case of head loss, if we have a parallel pipes, their head loss are equal. It means that the head loss here at pipe number 1, head loss at pipe number 2, and pipe number 3 are equal, okay, regardless of their diameter, length. Since they are in a parallel connection, their head loss are equal. So it means that all the values that we can compute on pipe 1, pipe 2, and pipe 3 are the same head loss. Okay, but unlike in series, okay, in series the head loss they are not equal. Okay, but only if we want to determine the total head loss, we add the 3. On the other hand, their head loss on this series of pipe on these parallel pipes are the same, but if there is an additional pipe here on the inflow and on the outflow, and there are let's say this is HF4, HF5 head losses on both the inflow and outflow pipe. So as a whole, if we are going to consider or determine the total head loss, we will just simply add the head loss at the inflow. Then how about the head loss here? So since they are all the same, we can just take one head loss, either head loss at pipe 1, pipe 2, or pipe 3, and head loss on the outflow pipe. Okay, so if there is an additional pipes on the inflow and outflow, okay, we can simply take this as a series of pipes again. Okay, you take it as a whole, the parallel pipes. You take it as a one pipe, and when you determine the total head loss, just add the three. This one, this one, this one. But again, for parallel pipes, their head loss are the same. Okay, their head loss are the same. Because we can use that property in solving some unknown values in a problem. Okay, so let's solve now some sample problems. Problem number 1. Water is pumped through a 500 mm diameter circular pipe. So given diameter is 500 mm. It is 800 meters long at a velocity of 2 meters. Okay. Velocity 2 meters. Letter A, determine the head loss using Darcy-Weisbach equation if we have f of 0.02. So using Darcy-Weisbach, we have a given mean velocity, so we will use the formula FL over D V squared over 2G. H of F is equals to F is 0.02, L 800 meters, diameter, that is in millimeters, so divided by 1000, 0.5 meters. V is 2 meter per second, 2 meter per second raised to 2 over 2 times 9.81 meter per second squared. So H of F is equals to, okay, 800. $6.524 okay, meters. Next, for letter B, this is your answer. Letter B, using Manning's formula, if we have a roughness coefficient of 0.013, so Manning's formula, H of F equals to 6.35 n squared LV squared over D raised to 4 over 3. H of F is equals to 6.35, 0.013 raised to 2. The length is 800. Then V 2 meter per second raised to 2 all over D, which is 0.5 raised to 4 over 3. So let's solve that now. Zero 0.5 to 4 over 3. So the head loss using the Manning's formula, 8.653 meters. That's the answer for letter B. For letter C, determine the head loss using Hazen-Williams. So C is 110. Okay, C1. So the given formula in Hazen-Williams is in terms of discharge, which is 10.67 LQ raised to 1.85 whole over C1 raised to 1.85 T raised to 4.87. So we can compute the discharge by solving the velocity using the velocity given. If we have a diameter of 500. Okay, take the area of that, multiply to the velocity in order for us to determine the discharge. Okay, so the answer is 0.3927 cubic meters per second. Substitute in this formula 10.67, L 800, Q 0.3927 raised to 1.85 over C1 110 raised to 1.85, T 0.5 is to 4.87. So H of F is equals to 1.85. Okay, the answer is 7.408 meters. Alright, so that's how you solve the head losses on H formulas that we use in this problem. Okay, next problem. Number 2. Two pipes, each 300 meters long, are connected in series. The flow of water through the pipes is 150 liters per second with a total frictional loss of 15 meters. If one pipe has a diameter of 300 mm, what is the diameter of the other pipe? Neglect minor losses and assume that F is 0.02 for both pipes. So it means that we are going to use here Darcy-Weisbach because we have a given friction factor of 0.02. Okay, so we have two pipes connected in series. Say pipe 1 and the other pipe unknown if we have a larger or smaller pipe. At a given length they are the same, 300 meters. Say L1, this is L2. Okay, the flow of water through the pipes is 150 liters per second, or in cubic meters 0.15 cubic meters per second. So that's your discharge. So since they are connected in series, the discharge in pipe 1 and pipe 2 are just the same. Then we have also given total frictional loss of 15 meters. It means total head loss of 15 meters. Okay, we have a given head loss of 15 meters from pipe 1 to pipe 2. Again, as we recall, the total head loss on series of pipe is just the sum of their frictional losses on each pipe. Okay, so it means 15 meters is equals to HF of 1 plus HF2. So that's an equation 1. So how can we determine the head loss of pipe 1 and pipe 2? Okay, so where can we get the values for that? So using Darcy-Weisbach, say considering the first pipe, we have here a given length, also diameter of 300 mm. Okay, so diameter of 300 mm using Darcy-Weisbach, and we have a given discharge Q. We can use the formula of HF is equals to 0.0826 FLQ squared over T raised to 5. This is in SI units. Okay, substitute now. The given values 0.0826 F 0.02 L length. Okay, L1 T1 L1 is 300. Q should be in cubic meters per second, 0.15, and a diameter of 300 mm, so that's 0.3 meters raised to 5. So the head loss in pipe number 1 is squared. Okay, this is squared 0.3 raised to 5, 4.589 meters. Okay, so now using this equation number 1, we substitute the values and we can now determine the head loss at pipe number 2 by subtracting the total head loss by the head loss at pipe number 1. So 15 meters minus 4.589. Okay, head loss at pipe number 2 is 10.411. Okay, so we can use that now in solving the diameter of the second pipe. Okay, so h of 2 equals to, using the same formula, 0.0826 FL2 squared Q squared over D2 raised to 5. Okay, so we solve diameter 2. Okay, cross multiply D2 and 2, just interchange them. We will have 0.0826 F squared Q raised to FL2. Okay, this is not squared, sorry, L2 Q squared over HF of 2. Then take the fifth root of both sides. Okay, that can determine the diameter. Okay, so the fifth root of 0.0826 F, same, 0.02 L2, they are 300 meters also. Q, the same. Okay, same discharge, series pipe, 0.15 cubic meters per second raised to 2 all over h of f of 2, 10.411. Okay, the diameter of the second pipe is root of fraction 0.0826, 0.02, 300, 0.15 over 10.411. Okay, 0.255. Okay, 255 meters, or in millimeter, just multiply it by 1255 millimeters. So this is your final answer. Okay, problem number 3. A pipe network consists of pipeline 1 from point A to B. So let's draw that. Let's say this is your pipeline number 1 from point A to point B. Pipe 1 to B. Okay, let's change the color to orange. This is pipe number 1, and we put labels. And from point A, this is your point B. Then at B, point B, it is connected to pipelines 2 and 3. So we have two pipes, pipes 2 and 3. Okay, let's say this is your pipe 2, pipe 3, where it merges again at joint C. So it means, okay, let's continue this. Your pipe 2 and 3, says there, it merges at point C to form another single pipe at point D. Okay, so means that this is your this is your pipe number 2, this is pipe number 3, and this is your pipe number 4. This is point C, this is point D. Okay, so as you can see, from a single pipe we form parallel pipes 2 and 3 and merges again on pipe 4. So if the flow rate, given flow rate from point A to point B is 10 liters per second divided by 1000, 0.01 cubic meters per second, and assuming the given frictional factor F is 0.02 to all the pipes, determine the flow in each pipe if the total head loss and determine also the total head loss from point A going to point D. Okay, so I know some of you are slightly familiar in how to solve the same type of problem, especially on circuits in physics. So here, using the given principles again and discharge and head losses, we also use the same principle here in pipe connections. Okay, so we do the same solution from there. As I recall, we use the Kirchhoff's law, I think, and here we just consider the discharge and the head loss. Okay, these two parameters only, and like in physics we have the voltage, current, and resistance. So I think here in solving pipe networks, it is easier as compared to circuits. Okay, so going back here, we are required to determine the flow rate in each pipe. Okay, so we have a given flow rate of 10 liters per second. So it means, okay, if we are going to add a table here, okay, add a table here for the discharge Q in cubic meters per second. Okay, we can say that pipe number 1 has a discharge of 10 liters per second or 0.01. So it is separated into two pipes 2 and 3, then merges again in pipe 4. So it means that pipe 4 has the same discharge as pipe number 1. Okay, unless there is another pipe linking to other direction. But here, since the pipes merges again into a single pipe, that means the amount of water that will travel here within this pipe network is just the same. So it means the discharge here at point of pipe number 4 is also the same as pipe number 1. Only that here in pipe number 2 and 3, we will have different values for discharge because they are in parallel connection. So it means that the discharge here at pipe number 1 is distributed to pipe number 2 and pipe number 3. So Q point 1 is equals to the sum of their discharges. Okay, so this is equation 1. We also have a given frictional factor for each pipe, 0.02, so we can consider that later on. Okay, 0.01 is equals to Q2 plus Q3. This is your equation 1. So now since we have values for the discharges at pipe 1 and pipe 4, okay, considering their head losses, H of F, say make another table. At pipe number 1, we can now easily determine the head losses at pipe number 1 and pipe number 4 because we have discharges, pipe 1 and pipe 4. So now we can now use the frictional factor. So HF of 1 equals to, we have given Q. So HF of 1, 0.0826 FLQ squared over D raised to 5. So 0.0826 F is 0.0202 plus length. That's the length for pipe number 1. Length for pipe number 1 is 3000 meters. FLQ 0.01 cubic meters per second squared divided by the diameter. We also have a given diameter of 200. Okay, is it in mm? In mm, so that's 0.2 meter is to 5. So the head loss at pipe number 1 is okay 1.54875 meters. Okay, next HF of 4, same formula, FL 4 Q e raised to 5. Okay, diameter for pipe number 4, diameter for pipe number 1, 0.02, diameter for pipe number 4, 2800, 0.01, same discharge, divided by diameter is 0.4 because we have 400 mm diameter. Okay, so let's just change this to 0.4 and this one 2800. Okay, 0.045 0.4517, okay, meters. That's the head loss at pipe number 4. Now the problem now is to determine the head loss at pipe number 2 and pipe number 3 because we don't have the discharges on pipe number 2 and pipe number 3. So how can we determine those values. So let's say we solve the head losses at pipe number 2 and pipe number 3 using the same formula. Okay, HF of 2 equals to 0.0826 F L pipe number 2 Q2 and diameter for pipe number 2 raised to 5. Okay, so we substitute. Okay, substitute 0.0826, 0.02 L, pipe number 2 is 2200, Q2 is unknown, squared to be divided by diameter, point is 300, 0.3 raised to 5. Okay, so let's solve now the coefficients because we have one variable Q2. So what will be the equivalent coefficient of this variable Q2? Let's solve this. Values. Okay, 2 is to 0.0826, 0.02, 2200, 0.3 raised to 5. Okay, we have an equation. HF of 2 is 1495.638 Q2. Okay, raised to 2. So this is an equation. It's equation 2. Next, when we solve the head loss on pipe 3, so say we directly substitute 0.02. The length on pipe 3 is 3200. Q3 equals to 2 to be divided by diameter on pipe number 3, 200, 0.2 raised to 5. Okay, that is equals to, okay, so this HF of 3 is equals to okay. HF of 3 is 16,520 Q3 raised to 2. Okay, this is equation 3. So we have head loss equation for pipe number 2 and pipe number 3. So based on our lecture, if we have parallel pipes, their head loss are the same regardless of their length differences and their diameters. So it means the head loss at point 2 is equals to the head loss on pipe number 3. So we make an equation 1495.638 Q2 squared is equals to 16,520 Q3 squared. Okay, so we have this equation. So now what we are going to do next is to find another equation to express this into a single variable. So going back to equation 1, we have this equation 0.01. Okay, right, that 0.01 equals to Q2 plus Q3. So from that, we can substitute from equation 1 going to this equation, it's equation 4, in order for us to determine one variable, or the other way around, from equation 4 going to equation 1. Okay, so let's say we substitute from equation 1. Let's say we find first Q2, so express Q3 in terms of Q2, so that's 0.01 minus Q2. Then substitute, so equation 5 in equation 4. Okay, 1495.638 Q2 squared is equals to 16,520. Q3 is 0.01 minus Q2 squared. Okay, so the unknown variable only is Q2. So I will directly solve this class. 1495.638. 495.638. Okay, variable x and 16,520, 0.01. Okay, so for x, we have two possible answers, 0.007687 or 0.014339. So based on the two answers, what do you think is the best answer? Okay, or what is the most suitable answer for the discharge at point 2? Okay, so going back here, as we can see that the discharge, when we have a parallel connection from pipe number 1, the discharge at pipe 1 is distributed to pipe number 2 and pipe number 3. So it means that the discharge at point 1 is the sum of discharge at point 2 and point 3. So it means that the discharge of point or pipe 2 and 3 should not exceed the discharge at pipe number 1, right? Because the discharge is just distributed from pipe number 1. So based on the two answers, since we have here quadratic equation that can be formed because the variable is in the second degree, so there are two possible answers. The most realistic answer that we can have here should have a discharge that will not exceed the discharge at pipe number Q1, which is 0.01 cubic meters per second. So based on the two answer, 0.014 is greater than 0.01 cubic meters per second, which is the discharge for pipe number 1. So this is incorrect. Okay, this is incorrect. But the correct answer for the discharge is 0.007687 cubic meters per second. That's the discharge for pipe number 2. Now, for pipe number 3, you can simply solve this using this equation number 5. Okay, Q3 is equals to 0.01, then subtract the discharge at point pipe number 2, which is 0.007687 cubic meters per second. So the discharge of pipe number 3 is 0.01 minus 0.007687. The answer is 0.002313 cubic meters per second. Okay, that's in cubic meters per second. So let's fill up this table. Okay, pipe number 2, 0.007687. Pipe number 3, 0.002313. Okay. How about the head losses of each pipe. Okay, we will also determine that. HF on pipe number 1, we have 1.549. Okay, we use 3 decimal places, and 0.045 on pipe number 4. So they have given discharges. So for pipe number 2 and 3, we can just simply substitute the computed discharges Q2 and Q3 on our equation number 2 and equation number 3. Okay, so using equation number 2, can now determine the head loss on pipe number 2, which is 1495.638. Q2 is 0.007687 raised to 2. So HF2 is equals to times 0.007687 raised to 2. 0.08838 meters. That's the answer. Then for equation number 3, equation 3 can now determine the head loss on pipe number 3, 16,520 times Q3. Q3 is 0.002313 cubic meters per second raised to 2. Okay, 16,520 times 0.002313 raised to 2. This is okay, the same, just to check, 0.8838 meters. Okay, they have the same head loss because they are parallel, 0.08838. Okay, let's fill this table. 0.0884 if we use 3 decimal places. Okay, so these are your answers for discharge and head losses for each pipe. So now we are also required to determine the total head loss. Okay, total head loss from point A to point D. Okay, the total head loss can be referred from this flow from point A going to point D, from pipe 1, pipe 2 to pipe 4, or from pipe 1, pipe 3 to pipe 4. So based on the two flows that I've drawn, it will give you the same values for head loss because pipe 2 and 3 are just parallel. So let's say I consider this flow for the total head loss from point A to point D. So just take the sum of the 3 pipes. Okay, so we will consider this as series of pipe. Okay, from point 1 going to point 2 and point 4. So just add the head losses of the 3. Okay, or we can use this also, this direction, flow from pipe 1, pipe 3 to pipe 4. They are just equal for the total head loss. Okay, so I consider pipe 2 on the parallel pipes. I considered pipe number 2. So just add the 3, 1.54875 meters plus 0.08838 meters plus the last 0.04517. So the total head loss from point A to D is 1.54875 Okay, total head loss is 1.6823 meters. So that's the answer. Okay, next. Okay, last example. Total head loss from point A, so this is point A, to point E is 15 meters. Okay, from point A to E, 15 meters. Find the discharge on each pipe, assuming that the friction factor is 0.02 for all pipes. So, given length and diameter for each pipe is on the table. Now let's make some equations basing on the flow rate first. Okay, so based on the figure, from point A to point E, we have a discharge Q1 here, then distributed to Q2. We have parallel pipes Q2 and Q3. Then Q3 at pipe number 3, it is connected to another pipe, so it is in series, pipe 3 and pipe 4. So discharge at pipe number 4 and merge again at pipe number 5. So basing on the discharge, we can say that the discharge at pipe number 1 is equals to discharge at pipe number 5, or the inflow is just equals to the outflow. Equation 1. Then from pipe number 1, the discharge is distributed to pipe number 2 and pipe number 3. So the sum of discharge and pipe 2 and 3 is equals to discharge at pipe 1. Then pipe number 3 and pipe number 4 is in series connection. So we can say that their discharge are the same. So Q3 is equals to Q4. So we're now okay on the discharge distribution equations for discharge. We can also make an equation using Q2, Q4 is equals to discharge at pipe number 5. You can also make an equation. Okay, so these are your equations using discharge. How about the head loss? Okay, so we have parallel pipes here. Pipe number 2 is parallel to pipe number 3 and 4. Okay, take pipe 3 and 4 as a whole, and this pipe 3 and 4 is parallel to pipe number 2. So if we take the total of head loss on this series connection pipe 3 and 4, okay, this is parallel to pipe number 2. So if we make an equation, pipe number 2 head loss is equals to the head loss of this pipe 3 and 4. So just take the sum of the two pipe. Okay, head loss 4. So that's another equation. Then we have a given total head loss of 15 meters. So we can use this direction of flow from pipe 1 to 5 to determine the total head loss, or we can use this flow from pipe 1, 3, 4 to 5. So the easier way is from pipe 1 to pipe 2, then pipe number 5 for the total head loss from A to E. So HF of 1 plus HF of 2 plus HF of 5. Substitute 15, HF1, HF2, HF5. Equation number 6. So these are your equations, okay, that can be used in solving the required, which is to determine the discharge on each pipe. Okay, so let's now solve using the formula for the head loss using Darcy waste back, because we have a given friction factor. So for pipe 1, using 0.0826 FLQ squared over d raised to 5 as our general formula. Okay, for pipe number 1, substituting the values, 0.0826 F 0.02, yes, L for pipe number 1 450, Q, do we have a given Q? None, so Q1 squared over diameter 600, so 0.6 raised to 5. Solve this. 0.6, 0.0826, 0.02, 9.56 Q1 squared. Then for head loss on pipe number 2, the length is 600, Q2 squared over diameter 500. Okay, 31.72 or 7184 Q2 squared. Then for pipe number 3, 0.02, length 360, Q3 450. Okay, 360, 32.229. Okay, just use 3 decimal places. HF4 0.0826 480. It's 450 also. 42.97 972. The last is HF5, length 540, diameter 600. Okay, Eleven. So here are your equations in solving the head losses. So next one that we will do is from equation 6. Okay, equation 6. We have 15 equals to hf1 plus hf2 plus hf5. So substitute now hf1, hf2, and 5. This values 15, 9.56 q1 squared plus 31.718 q2 squared plus 511.472 q5 squared. So we have this equation with 3 unknowns. So basing again from the equations that we have derived earlier, we can substitute other values to eliminate some unknowns. So now we will base in equation number 5. Equation number 5, we have hf2 is equals to hf3 plus hf4. Then substitute again. hf2 is 31.718 q2 squared equals to 32.229 q3 squared plus 42.972 q4 squared. Okay, but as you can see, discharge at q3 is equals to the discharge at pipe number 4. So we can eliminate one variable. Let's say q4 is equals to q3, so we substitute q4 by q3. 31.718 q2 squared is equals to 32.229 q3 squared plus 42.972. This is q3. So combine like terms, we have 42.972, 75.201 q3 squared. So this is another equation that we formed. Let's say this is equation number, okay, we have equation number 6, equation number 7. This one is equation number 7, this is equation number 8. Okay, then what we will do next is again use another equation here. Equation number 2. So actually, since we have an equation here, equation number 8, in order for us to eliminate the exponent squared, we can also take the square root of both sides. Okay, if we take the square root of both sides, okay, the exponent 2 will be eliminated. Okay, square root of 31.7 to make this equation simpler. So 5.632, 1.632, 6318, 187 q2 is equals to square root of 75.201, 8.67185 q3. Then we express q3 in terms of q2. Okay, divide both sides, or the other way, q2 in terms of q3. You can do that also. Okay, or we divide 8.67185, 8.67185, 5.63187 over 8.67185, 0.649. Q2 is equals to Q3. Okay, this is your equation number 8. Okay, equation number 8. It's much simpler. Okay. Next, we will base now from equation number 2, which is Q1 is equal to Q2 plus Q3. Okay, so we write it here. Equation number 2, Q1 equals to Q2 plus Q3. Since Q3 is equals to 0.649 Q2, Q1 is equals to Q2 plus 0.649 Q2. Q1 is equals to 1.649 Q2. Okay, we have another equation, equation number 9. Then let's refer again from our equations here. From equation number 7, which is 15 equals to 9.56 Q1 squared plus 31.718 Q2 squared plus 11.472 Q5 squared. Okay, we can now substitute Q1 in terms of Q2. Okay, but before we substitute that, as referred in equation 1, Q1 is equals to Q5, the discharge at discharge pipe 1 is equals to discharge at pipe 2. So we can substitute this as pipe number 1 and combining like terms, it is 9.56 Q1 squared plus 11.472 Q5 substituted by Q1 because they are equal. We have now variable of 9.56 plus 11.472, 21.032 Q1 squared plus 31.718 Q2 squared. So we've already eliminated Q5. So from that, we can now substitute equation 9 here in equation 7. So 15 equals to 21.032 multiplied by 1.649 Q2. This is raised to 2 plus 31.782 Q2 squared. So the only unknown now is discharge at pipe number 2. So let's directly solve that. 15 equals to 21.032 squared. Okay, two values, we take the positive one, which is 0.411, 0.410541 cubic meters per second. That's your discharge at pipe number 2. Okay, so from that we can now solve the other discharge in this pipe. So for Q1, that's 1.649 times 0.411. So Q1 is 0.678 cubic meters per second. Then that is also equal to pipe number 5. This is also equal to pipe Q2 is also equals to what? Okay, Q3 is equals to Q4. So let's find discharge at pipe number 3. So Let's refer on equation number 8. Equation number 8, Q3 is equals to 0.649 times Q2. Q2. Q2 is 0.649 times 0.411. Okay. Q3 is equals to 0.267 cubic meters per second. This is also equals to discharge at pipe number 4. Okay, so to check, we can check that when we add pipe number 2 and pipe number 4, the discharge of pipe number 2 and pipe number 4, so our computed the value should be equals to Q1, or as we determine Q5, we take the sum of Q2 and Q4. It should be the same with discharge at pipe number 1, or the inflow discharge. Okay, so when we add the two, Q2 plus Q3, which is 0.411 plus 0.267, we have a 0.678 discharge for pipe number 5, which is equals to the discharge at pipe number 1, 0.678. So we have the correct answer. Okay, so that ends our lecture in fluid flow in pipes. Thank you for watching. God bless.